So good afternoon. Let us start our lecture today. I posted the practice exam online, and today I want to correct this exam, so this practice exam, so that you know what is going on in the exam.
So
right.
This is the practice exam that we're supposed to be doing here. What we're about to do.
I'm supposed to be. I will do it, not you. All right. So this is the practice exam, and I will do it for you.
Okay.
All right.
All right.
And the test will be like this.
Okay.
All right. So I'm gonna explain to you what is what should you prepare for the exam. Right. In the exam, you're gonna have 3 problems. So the problem 1 will be 10 points. So in the problem 1, that will be exactly like the homework, right? You're going to have u second plus lambda u is 0. This is an eigenvalue problem, and you have 2 boundary conditions on AB. Is it going to be different from the homework? Because I'm going to replace the boundary condition by something else. The framework will be the same. The difference is the lambda, right? So you can have ua is 0 and ub is 0, or u prime a is 0, and this is also u prime b is 0, or ua is 0 and u prime b is 0. Right? So the first question is going to be the what kind of problem is it?
The eigenvalue.
Eigenvalue problem, right? So the first problem will be eigenvalue problem. The framework will be the same. So it's gonna be exactly like in the homework. You're gonna solve u second plus lambda u is equal to 0. The only difference is boundary condition. You plug several kind of boundary condition here, and you gonna have different lambda, but the framework is the same, right? So what I'm checking is if you understand how to find eigenvalue and eigenfunctions. So here you can have plus or minus. If you have plus, if you have minus, this is something that we did in class. If you have plus, then you have to change the sign of lambda. You just do the work of changing the sign from minus to plus, right? So when lambda is positive in class, in the homework it is negative, so in the exam I can change lambda. All right? And then, so of course, I can put an and here, but it doesn't matter. This is the first problem, right? Eigenvalue problem, it is exactly like what we did, except the boundary condition will be changed, right? Problem number 2. You're gonna solve PDEs. Solve boundary value problem. Boundary value problem. So you're gonna ask to solve u second of x is equal to something with some boundary condition, right? 0 or whatever. Right? So in the second problem, you're gonna solve the boundary value problem, and in the first problem, you only need to solve the eigenvalue problem. And how do you solve the boundary value problem in the second questions?
You have to set up the eigenvalue.
Yes. You solve the eigenvalue problem, right? You set up the eigenvalue problem, you find a basis to expand them. This is number 2. And question number 4, which is optional. So the total points is 20. If you can solve everything, you're gonna get 30, which is optional, which is also 10 points. So this problem, you can have a look into practice problem, problem 2 in our practice problem, in practice exam. Which is something that we are going to do today. All right? And for the last one, it is going to be a hard question, but I give you in advance the form. All right? So you're gonna solve something like u second plus bu prime plus cu is going to be equal to something plus boundary value. So I'm gonna put alpha. This is alpha, beta, gamma going to be equal to something plus some boundary condition like ua is equal to ub is equal to 0. And this is similar to problem 1 in the practice exam. All right, so for this kind of problem, I gave you already one example in the practice exam, which is the first problem in the practice exam. But I'm not going to solve it in class. I mean, I'm gonna solve it after the exam. All right, so yes?
For problem 2, you also want us to expand to solve eigenvalue problem.
Right. You have to expand on eigenvalues and on eigenfunctions, but this is much more complicated. This is harder. This is the simple case. This is harder because you're gonna have all of the derivative, right? Here you have only u second. Here you have u second, u prime u. All right. So this is harder, but I gave you one hint, which is problem 1 in practice exam 2. If you solve this, you will be able to solve the optional problem in the test. And then if you solve 3 questions, you're gonna get 30 points over 20, right? The highest score will be 20, but if you solve everything, you're gonna get 30. And these 10 extra points will be accumulated, right? Because we're gonna add everything together. And so this is a homework. And this is nothing but a part of this problem, right? Because when you want to solve a boundary value problem, you're gonna have to solve the eigenvalue problem. All right? So basically, in this class, we're gonna cover problem 2 in practice exam 2. All right? And in this problem, I'm gonna solve one of the homework questions as well. Any questions? It's clear? All right. So let us try to go to this one. Right. So in problem, this is problem 2. All right. So using the method of eigenvalue eigenvectors, so u second is equal to minus x on minus 1, 1. U minus 1 is u1. U minus u prime 1. All right? So, step number 1, eigenvalue problem. Can you tell me what is the eigenvalue problem associated to this boundary value problem? Yes?
Second equals lambda.
Yes, you can have n, you don't have to put n, right? We will see n later. And what is
minus 1 equals
n?
3 prime minus 1 equals
Yes. Can you sign the back of the paper, please? All right, so you have to, the first step is to identify the eigenvalue problem, right? Because the eigenvalue problem will give you the basis. Will give you the basis, right? All right, so the associated eigenvalue problem is the following. The first line is always like this. You're gonna find lambda, which is an eigenvalue, phi, which is the eigenfunction. All right. In the first step, you always have to find phi second is equal to lambda phi. Lambda is the eigenvalue, you don't know. Phi is the eigenfunction, you don't know. Your job is to find a function whose second derivative is itself times a constant that you don't know, right? Questions? So those are the two unknowns. Now, the boundary condition will be the same. You're gonna have u of minus 1 is equal to u1. You replace u by phi. You're gonna have phi of minus 1 is phi1. U prime minus 1 is u prime at 1. So you replace u by phi. You're gonna have phi prime minus 1 is phi prime at 1. Right? Any questions? So basically this is one of the problem that we have in homework. Right? So this is one of the homework problem. So what is the characteristic equation for this equation? Yes?
X squared equals lambda.
Yes. Can you say at the back of the paper, please? So the characteristic equation x squared is equal to lambda. Right? So we have to consider three cases always. Case number one. Case number one. Lambda is positive. Alright? So, of course, if here I have this, then you have to consider lambda negative, right? This is the other one. Now, what happens when lambda is positive? Yes?
We have 2 words.
You have two solutions. Yes, can you sign the back of the paper, please? So you have x1 is square root of lambda, and x2 is minus square root of lambda. What is the solution in this case? Yes?
C1 e to the square root of lambda x plus C2 e to the minus square root of lambda x.
Yes, can you sign at the back of the paper, please? So you're gonna have what? You're gonna have phi of x will be C1 e to the square root of lambda x plus C2 e to the minus square root of lambda x. All right? This is the form of the equation, of the solution, right? Again, you have to memorize the table that I gave you. When lambda is positive, x1 will be square root of lambda x, x2 will be minus square root of lambda. So the solution will be C1 e to square root of lambda and C2 e to minus square root of lambda x. Right? So, what is the next step? Yes?
We plug in our boundary condition for the just b negative 1 equals b of 1.
Yes, can you sign at the back of the paper, please? Now you plug the boundary condition, right? You plug the boundary condition. Phi of minus 1 is equal to phi 1. This means that C1 is to the square root of lambda minus 1 plus C2 e to the square root of lambda 1 is equal to C1 e to the square root of lambda plus C2 e to the minus square root of lambda. Alright? So the boundary condition says that phi minus 1 is equal to phi. Right? So basically, this is the questions that I'm asking you in the, this is the problem that I asked you in the first questions of the test. You have to solve the eigenvalue problem only. And it's going to be exactly the same except that I changed the boundary condition. Alright? You're going to have phi of minus 1 is equal to phi 1. So I replace minus 1. I have C1 is square root of lambda times minus 1 plus C2 is square root of lambda times 1. This is equal to C1 is square root of lambda plus C2 is square root minus lambda. So then you have C1 is square root minus lambda plus C2 is square root lambda is equal to C1 is square root lambda plus C2 is square root minus lambda. Alright? Now what can I do next? Yes?
Me?
Both of you. So you first and then.
Okay, I think you can have C1 e to the negative lambda minus C2 e to the negative lambda in one side and then move the over and then factor
Yes.
out e to the lambda.
And you, but
I was gonna say maybe never set it equal to 0 and factor it out.
right. Can you both sign the paper, please? So you're gonna put all of the C1 together, right? You're gonna put all of the C1 together and all of the C2 together. So I have C1 is the square root minus lambda minus e to square root minus lambda plus C2 is square root lambda minus e square root minus lambda. And this is equal to 0, right? I'm gonna put all of the C1 together and I'm gonna put all of the C2 together. So when I put all of the C1 together, I have C1 here, so I have C1 is square root minus lambda minus e square root lambda, and this is C2, so I have C2 is square root lambda minus e to the power minus square root lambda, right? So what is the next step? Yes?
If you take the negative out of the second parenthetical term, then you'll end up with the same term inside of both parentheses, so you can end up with C1 times that minus C2 times that.
Right. Can you sign the back of the paper, please? So you see that this guy is the minus of this guy, right? So I'm gonna write this way. So you have e square root lambda minus e square root minus lambda plus C2 is square root lambda minus e minus square root lambda, and this is 0. So I can group the two things. I have C minus C1 is square root lambda minus e square root minus lambda, and this is 0. Alright, so I explain again. After I group C1 and C2, I have C1 times this guy plus C2 times this guy. But I notice that this guy is the minus of this guy. Alright? I write this guy like minus of C1 is square root lambda minus is minus lambda, and then keep this guy the same. Right? Now, this and this, they are both the same function, right? I can put them as a common factor. So then I have C2 minus C1 times this guy is 0. What can I say? Yes?
The C2 minus C1 is 0, so C2 is equal to C1.
Yes. Can you sign the back of the paper, please? So this means that C2 minus C1 is 0, which means that C2 is equal to C1. Why can I say that? Yes?
Because you know the other term is always going to be positive, so it can't be equal to 0, so therefore C2 minus C1 has to equal 0.
Can you sign the back of the paper, please? Because we know that this guy is always positive, right? Reason. Square root lambda minus e square root minus lambda is positive. This is always positive. So you remember why this is positive? Why? Yes?
Because e to the square root of lambda is always greater than 1, and e to the negative square root is always less than 1.
Yes. Can you sign the back of the paper, please? So you have e to the square root of lambda is always positive than 1, greater than 1, and this is greater than the inverse of itself. Right? So you know that this guy is always greater than 1, and 1 is always greater than the inverse of something which is greater than 1. So now we have C1 and is equal to C2. I'm going to plug everything back into the equation, right? To the solution. Right. So you're going to have Px will be C1 is square root of lambda x plus C2 e to square root minus lambda x, but C1 is equal to C2. So I have square root of lambda x plus C1 square root minus lambda x. All right? So this is the general form of the solution, but we know that C1 is equal to C2, so I replace C2 by C1, and I have C1 is square root of lambda plus C1 is square root minus lambda. Right? What is the next step? Yes? Yes. Can you sign the back of the paper, please? Now I'm going to take the derivative and I'm going to use the second boundary condition. Right? So this prime will be C1 square root of lambda is square root of lambda x minus C1 square root of lambda is square root minus lambda x. Alright? So I'm going to take the derivative of this guy. The derivative of this guy gives me C1 square root of lambda is square root of lambda minus C1 square root of lambda exponential. Right? So the first The first question in the exam will be like this. I just replaced the boundary condition by something else, so the details of the computation will be changed, but it's gonna be the same framework, all right? Now I'm gonna have phi prime at -1 is equal to phi prime at 1. Right, so I'm gonna replace everything inside. So I have square root of lambda e to the minus square root of lambda minus c1 e square root of lambda e to the power square of lambda, and this is equal to c1 square root of lambda is square root of lambda minus c1 square root of lambda is minus square root of lambda. Right? So this guy is the derivative phi at -1, right? So I replace -1 here. I have minus square root of lambda. I replace -1 here. I have square root of lambda. This guy, I replace 1 here. So this guy, when I replace 1, actually 1, I got square root of lambda. When I replace this, when x is 1, I get this one. All right? Questions? It's clear. What is the next step? Yes?
You combine terms on one side, so you'd end up with 2c1 square root lambda times e to the negative square root lambda minus e to the square root lambda equals 0.
Can you sign back the paper, please? So you combine this with this and this with this, right? So you combine this guy with this guy, so you have 2c1 square root of lambda e to the power minus square root of lambda is equal to 2c1 square root of lambda is square root of lambda. Right? Right, so I combine c1 square root of lambda exponential minus square root of lambda with this guy. So this guy and this guy, they're the same. This is why here I have 2. I combine this guy, and because they are the same, here I have the number 2. All right? Now, what is the next step? Yes?
Can you this in this set of equals to 0?
Yes, can you say the microphone of this? So you have 2c1 square root of lambda e square root of lambda minus e square root of lambda is 0. All right? So I subtract the two sides. I put the 2c1 square root of lambda as the common factor. What can I say about this? Yes?
Well, again, you know that the e term is always going to be positive for the same reason, and we know that lambda is greater than 0, so you know that term won't be 0, so therefore c1 would have to be equal to 0, and then therefore c2 would have to equal 0.
Yes, can you sign the back of the paper, please? So this guy is always positive, right? This guy is positive because we consider lambda strictly positive. So, which means that c1 is 0, and because c1 is 0, c2 is also 0, so the function is 0. And this is not admitted, right? So we don't admit 0 as an eigenfunction. Questions? Now, let us start, let us do the second phase. The second phase will be lambda is 0. Right, so when lambda is 0, you're going to have phi second of x is 0, right? What can I say about phi? Yes?
A equals ax plus b.
Yes, can you say at the back of the paper, please? Because the second derivative of phi is 0. The first derivative has to be a constant, right? Which means that the function has to be ax plus b. All right? Okay, questions? Now, what is the next step? Yes? Yes, can you say at the back of the paper, please? All right, so the first boundary condition is phi 1 is equal to phi of minus 1. All right, so which means that I times 1 plus b is equal to a times minus 1 plus b. Alright? I plug 1 and minus 1 to phi. I find a times 1 plus b is a times minus 1 plus b. What can I say about, yes?
A equals 0.
Yes, can you sign the backup paper, please? So from this, you know that I can eliminate it 2b, so this means that 2a is 0, 0, so a is 0. Alright? Can you sign it? The first boundary condition, the first boundary condition said that phi1 is phi of minus 1, right? I'm gonna replace 1 and minus 1 here, so a times 1 plus b is a times minus 1 plus b. I remove the 2b, so 2a is 0, a is 0, right? So the function is b. What is the next step? Yes?
Can you take the second derivative?
Yes. Can you sign the backup paper, please? So the first derivative, right? So the first derivative of x is 0. But so for this one, the boundary condition is satisfied. Right. So it's automatically satisfied, which means that so this is a constant function. Right. So a constant function is an eigen function for lambda is equal to 0. Right? So b, so in this case, you know that any b satisfy the two boundary conditions, right? So if you take a constant function, you give the value 1 to b, then you're gonna have immediately phi1 is phi minus 1, and phi prime at 1 is phi prime at minus 1, and then the second derivative of phi is 0. So you know that all constant functions are eigenfunctions, right? But again, because the constant doesn't give any difference to the expansion, so I'm gonna say that okay, the eigen function is phi x is 1, right? So I can, because this is a constant, I can choose it to be 1, right? So I can remove the constant and put it to be 1. So the first eigenfunction is 1, and the associated eigenvalue is 0. This is why you always have to do this, because sometimes in the second case you're gonna have 1. All right. So in this case you have 1. Any questions on this? And the eigen lambda, the eigenvalue will be 0. So I'm gonna be now phi 0, x to be 1, and lambda 0 is 0. This is the first eigenfunction and the first eigen value that we found. The 0 is the index, right? So we're gonna have phi1, phi2, phi3 later. Clear? Right. So now case number 3. You have lambda is negative. So what happens when lambda is negative? Yes?
C1 for something square root of absolute value of lambda plus C2 sine absolute value of lambda.
Can you sign the backup paper, please? So when lambda is negative, you're going to have two roots, right? x1 is the square root of lambda, absolute value of lambda, and x2 will be I. Minus I square root of lambda. So these are the two solutions in this case. All right? So then Px will be C1 cosinus of square root of lambda x, and C2 sinus of is the next step? Yes?
How you bring in the value balance?
Can you send the the paper, please? So you're gonna use the boundary condition, right? So you're gonna have phi1 is equal to phi minus 1. All right? So you're gonna have C1 cosinus of square root of lambda plus C2 square sinus of square root of lambda is equal to C1 cosinus of minus square root of lambda plus C2 sinus of minus square root of lambda. All right? It's clear? You replace 1 here and you replace minus 1 there, right? So phi1 is equal to phi of minus 1, which means that you replace 1 here. This is the first line, and then you replace minus 1. This is the second line. Questions? It's good. Now, what can I say about those? Yes.
Isn't the cosine even, so the negative disappears and the negative comes out the sign?
Yes. Can you send back the paper, please? So you know that the cosinus of minus square root of lambda is the same with the cosinus of square root of lambda, right? So we have C1 cosinus of square root of lambda minus C2 sinus of square root of lambda. Right? I put minus here, so the cosinus of minus square root of lambda will be the same with the cosinus of square root of lambda. C2 sinus minus square root of lambda will be the same with minus C2 sinus square root of lambda. So these can cancel with this, right? And I group this guy and this guy. I'm gonna have 2 times C2 sinus of square root of lambda is 0. All right? So sinus of square root of lambda should be 0. Right? So what? Yes. So what values for lambda that I can omit? Yes.
Sine n pi would be equal to the square root of x to the variable.
Yes. Can you sign the back of the paper, please? So the sinus of this guy is 0, means that the n and this guy has to be n pi. Right? Square root of lambda is equal to n pi, which means that lambda is minus n pi squared. All right, because lambda is negative. Now I have to check the second condition. The second condition is what? The second condition is phi prime 1. So in order to do the second condition, I'm gonna have to take the derivative, right? So when I take the derivative, I'm gonna have C1 square root lambda cosinus of square root lambda x sinus sum plus C2 square root lambda cosinus of square root lambda x. All right? We're going to use the second condition. The second condition says that phi prime at 1 is equal to phi prime at minus 1. Questions?
I think I screwed up on the home result.
Sorry?
I think I screwed up on the home result.
Okay. I'm gonna show you one very important remark after we solve all of the eigenvalues and eigen vectors. Right. So you take the derivative of this guy, you have my square root lambda sinus, and then sinus derivative will be square root lambda cosinus. All right. Now we're gonna plug the boundary condition here. Right, so you have phi1 of 1 is equal to phi1 prime at minus 1. I replace 1 here. I have C1 square root of lambda sinus of square root of lambda x 1, sorry, plus C2 square root of lambda cosinus of square root of lambda is equal to C1 square root of lambda sinus of minus square root of lambda plus C2 square root of lambda cosinus of minus square root of lambda. All right? Yes?
There should be negatives in front of both the C1.
Yes. Thank you. Thank you. Thank you. Can you sign the paper, please? All right. So what can I say about this? Yes.
Cosine terms are gonna cancel out, and you can move the sine terms onto one side,
Yes.
because the negative inside the sign will move out.
Yes. Can you sign the back of paper, please? So now the cosinus and the cosinus here, they are the same, right? To be more precise, because the minus here combined with the minus here, I have C1 square root of lambda sinus of square root of lambda plus C2 square root of lambda cosinus square root of lambda, right? So the first step, I'm gonna change the sign, right? Here I have sinus minus square root of lambda. I have a minus and I have a minus, so I can cancel the two minus. I have sinus square root of lambda. The cosinus minus square root of lambda and cosinus square root of lambda, they're the same. Now, I'm gonna remove these two terms and I'm gonna combine the two terms here. So we have 2c1 square root of lambda sinus of square root of lambda is 0. But we know that square root of lambda is n pi, right? But since square root of lambda is n pi, so this boundary condition is automatically satisfied. All right. So from the first boundary condition, I found that square root of lambda has to be n pi. All right. But from the second boundary condition, I get C1 square root of lambda sinus square root of lambda is 0. But of course, this is satisfied with the value that we found in the previous step. So this boundary condition is satisfied. All right. So basically, what can I say about the function? What can I say about the function phi? Yes?
Is cosine n by x plus sine by x.
Yes. Can you say the back the paper, please? So because phi, so then from this finding, I have C1 is cosinus of n pi x plus C2 sinus of n pi x. All right? Yes?
So the negatives inside, you're just pulling, are you pulling it out to the front? That's why it cancels with the C1? Or how did you,
So the sinus of minus square root of lambda will be minus of sinus of square root of lambda, right? But I have the minus here, so they cancel.
okay, so then how over here did we go from C1 cosine of negative square root of lambda plus C2 sine of negative? Wouldn't there be supposed to be like another minus in front of the first?
So the cosinus of minus square root of lambda is the same with the cosinus square root of lambda.
Okay.
And the sinus is the minus sinus. So you have cosinus of I is cosinus of minus I. Right, they are the same, but sinus of I is minus sinus of minus I. All right? Right, so from this, I found that, okay, the eigenfunction has to be out of form C1 cosinus n pi x plus C2 sinus n pi x. All right? In other words, I can choose this guy and this guy because we're gonna combine the function, all of the constant together. We don't care about constant, so we choose the two. The two eigenfunction for lambda n minus n pi square cosinus n pi and sinus of n pi. We don't care about a constant, right? It's clear? Right. To summarize, the basis is what? The basis is. So what is the basis in this case? Excellent. Can you sign the back of the paper, please? Right. So in this case, you have a Fourier series, right? Very good. So from the case lambda is 0, you found the function 1. From this case, you found cosinus of n pi x and sinus of n pi x. So this is a Fourier basis. Right? So who can tell me why do we get a Fourier basis in this case? Yes?
Because the boundary value for one is what, -1, this is 1.
This is one thing, yes?
So, in the Fourier series, it has to be from -L to L, so that's why.
So yes, this is one thing. This is from -1 to 1, so the domain is symmetric. This is one thing. The second thing is what? Can you send the back of the paper, please? So you know that, okay, the eigenvalue problem that we have that we have is what? Phi second is lambda phi on -1 to 1, and then phi 1 is equal to phi -1. Phi prime at 1 is phi prime at -1. Right? Yes?
Since the boundaries are equal to each other, it's periodic.
Yes, can you sign the back of the paper, please? So there are two things. First, the domain is symmetric, right? And the second boundary condition, the two boundary condition, just simply say that the function is periodic, right? It's periodic. Right? So in this case, in some sense, this boundary condition tells you that we are dealing with periodic functions. And because we are dealing with periodic function, the only basis that is available is the Fourier basis, right? So this is why in the beginning of the class, we learn about Fourier basis, and then we learn about eigenvalue problem. And from this exercise, you realize that, okay, this eigenvalue problem, if you put into the context of periodic function, you find exactly the Fourier basis that we discussed from the lecture 1. Right? So in order to have a Fourier series, you need a periodic, a symmetric domain, which is from -1 to 1 or -L to L, right? So if I replace here to be L, if I replace not L, so yes, so let me put L, -L to L, right? And I do exactly the same step that I did. What kind of basis that I get?
You still get the
What is the form of that?
Right, it's just the form of the Fourier basis, like the 1 cosine and then n pi x over L.
Yes, in the side of the paper. So if I solve this eigenvalue problem on a domain which is from -L to L, and the boundaries, and you put a periodic boundary condition on L, you're going to get dividing by the same Fourier basis, but on for the interval from -L to L, which is 1 cosinus n pi x over L sinus n pi x over L, right? Which is the Fourier basis for -LL. It's clear? So basically, the eigenvalue problems is a general theory, and the Fourier basis is one special case, right? Questions? It's clear? Right. So this is also one of the homework, and basically for the first problem of the exam, this is what you have to do. For the second problem of the exam, this is also what you have to do, but you have to do extra work, right? So the extra work will be the following. So step number 2. Alright, so I write out the form of the equation. On minus 1, 2, 1, and u of minus 1, the 1 u prime at minus 1 is u prime at 1. Alright? So what is the next step? Yes?
Expansion.
Yes. Can you sign the back of the paper, please? So you do the expansion, right? Expand u on a Fourier basis. Alright? Questions? Right, so I'm gonna expand u on a Fourier basis, which is the following. So you have ux is a0 plus a1 cosinus of pi x plus b1 sinus of pi x plus a2 cosinus of 2 pi x plus b2 sinus of 2 pi x plus an cosinus of n pi x plus bn sinus of n pi x. Alright, so and this can be written like a0 plus the sum when n is going from 1 to infinity of an cosinus of n pi x plus bn sinus of n pi x. Alright? You just have to, in this case, you use the Fourier basis because this is what you found. You found a Fourier basis, so you expand the solution on the Fourier basis. Ux will be a0 plus a1 cosinus pi x, b1 sinus pi x, a2 cosinus 2 pi x, b2 sinus 2 pi x, an cosinus n pi x, bn sinus n pi x, right? And you also expand. So what is u second? Yes?
Negative x.
No, I want to know the Fourier expansion.
It'll be the summation of an times n pi, or negative n pi squared, cosine n pi x plus bn negative n pi squared, sine n pi x.
Can you sign the back of the paper, please? So we want to use the formula that we have, right? So you, in order to take the second derivative, you take a second derivative of this guy, that gives you the lambda, right? So this is going to give you the sum when n is going from 1 to infinity of an minus n pi squared. So, yes, so here you have minus n pi squared. You have cosinus n pi x plus bn minus n pi sinus of n pi x. Right? So when you take the second derivative, you multiply each coefficient by the eigenvalues. Right? Now, the next step is to expand x on this basis, right? So you're going to have c0 plus the sum when n is going from 1 to infinity of cn cosinus of n pi x plus dn sinus of n pi x. Now, I have to compute each of these guy, cn and dn, right? The next step is to expand minus x on the Fourier basis. C0, so how can I compute C0? This is the Fourier series, right? How can you combine it first? Yes?
It should just be 0, right?
This is 0, why?
You're taking the derivative of a constant. An, or a0.
No. I want to compute C0. There's no derivative here, right? Yes.
So you compare both equations, u prime of x and negative x, and say equal to each other, and comparing that c0 has to be 0.
No. Before that, I want to just to do the Fourier expansion of this guy. How can I compute the Fourier coefficients of the series, the Fourier series? Yes?
L1 over 2L is integral negative L to L f of x dx.
Yes, can you say the back paper, right? So this is 1 over L minus 1 of minus x dx. Alright, this is the formula of Fourier series. You remember that? So for Fourier series, the first formula is 1 over 2L, the integral from minus L to L of the function fx dx. This is how you compute the first constant of Fourier series, right? So for this one, you have the integral from minus 1 to 1 of minus x dx, and this is 1/2, and of course this is 0, y. Yes?
It's an odd function.
Yes, can you sign the back of paper, please? Because minus x is an odd function, so this has to be 0, since minus x is odd. All right? Now, at this step, what we do is we come back to the Fourier series lecture. So we how can I compute Cn? Yes.
1 over L from the integral of negative L of L of f of x times cosine minus to 0.
Yes. Can you sign the back of paper, please? So this is going to be integral from minus 1 to 1 of minus x cosinus of n pi x dx. So you remember how we obtain this formula? How can I obtain this formula for Cn? Anyone else? Yes?
By taking the inner product.
Yes. Can you sign the back of the paper, please? So you remember that in the first, before the first midterm, to compute the coefficient Cn, what we do is we multiply everything with cosinus n pi, right? Right, so it's exactly the same like what we are doing here. So review. So how do we review? So we obtain Cn by the following way. So you multiply minus x with cosinus of n pi x, right? Everything else drops out except the Cn, right? Cn cosinus n pi. Right? Plus 0 terms. 0 terms. Right? Because of orthogonality, you multiply minus x with cosinus n pi. The only thing that is leaving is this guy. The other one disappear. So then Cn will be minus x cosinus n pi x divided by cosinus n pi x cosinus n pi x. And this gives me the integral from minus 1 to 1 of minus 1 cosinus of n pi x dx dividing by integral from minus 1 to 1 of cosinus n pi x squared. And if you compute this out, this will be 1. So you can ignore that, and it gives you this guy, minus x cosinus of n pi x dx. All right. So this is exactly the same. It's always like that. You want to compute a coefficient, you use orthogonality. You multiply with the function, the basis function of that coefficient. Because of orthogonality, the other terms will be dropped. So finally, what is leaving is minus x cosinus n pi x and cosinus n pi x and cosinus n pi x, right? You compute Cn by dividing the two terms. But of course, when you compute this guy, it's 1. So here I don't have to care about that guy. Now, what is the value of Cn? Yes?
Also 0 because it's the odd terms in the function.
Can you sign the back of the paper, please? So this is also 0 because minus x is odd, cosinus n pi x is even. So odd times even is odd, right? So then we come back to the previous lecture. We know that, okay, integral of an odd function is 0. It's clear? Now, we're gonna compute dn. So what is the value of dn? Yes?
It would be the same function but with sign.
Yes. Can you say to make that paper, please? So this is going to be minus 1 to 1 minus x sinus of n pi x dx. Alright, so you replace cosinus to sinus. And in this case, it's not 0, but we have a way to simplify it. Who remember this? Yes?
You could say 2 times 0 to 1
Yes.
of the same thing.
Yes. Can you stand back the paper, please? So this is odd. This is odd. So odd times odd is even, right? And this means that you don't have to compute the whole thing. You only have to compute one interval from 0 to, right? Because minus x is odd. Sinus of n pi x is odd. So the product is even, right? So you know that minus x is odd. Sinus is odd. Odd times odd is even. So because this is an even function, so we go back to previous lecture, we know that, okay, if it is an even function and you integrate from minus 1 to 1, what you do is you integrate from 0 to 1 and you multiply that by 2. Right? Right, so now I'm gonna compute dn. Right, so dn will be minus 2 integral from x to 0 to 1 of x sinus of n pi x dx. Alright? It's good. How can I compute this guy? Yes?
You can do integration by parts.
Yes, can you say it like the paper, please? So I'm gonna use integration by part, right? So I have u dv is uv minus v du. Alright? In this case, u is always this guy. This is dv. Right? So because this is dv, I got since cosinus of n pi x over n pi x prime is sinus n pi x. Right? So now you use integration by part. You know that the derivative of cosinus n pi minus dividing by n pi is sinus. So I'm gonna use this formula there. I'm gonna have integral from 0 to 1 x d of minus cosinus n pi x over n pi. Alright? So I move the constant outside. I have minus 1 over n pi, so I have 2 over n pi integral from 0 to 1 of x d of cosinus n pi x. And now I'm gonna use this formula. I have 2 over n pi. Then I have x cosinus of n pi at 0 and 1 minus 2 over n pi integral from 0 and 1 cosinus n pi x dx. It's okay? I explain again. So here I want to compute the n, which is minus 2 integral from 0 to 1 of x sinus n pi x dx. I'm gonna use integration by part. So I observe that, okay, cosinus n pi x over n pi prime will give you sinus n pi. So which means that I can write sinus n pi x dx as d of minus cosinus n pi x over n pi. I can remove all of the constant outside, so I have 2 over n pi integral from 0 to 1 of x d of cosinus n pi. So this is u dv. Alright? U dv is equal to uv and v du. Right? U is x and dv is d of cosinus n pi. Right? So this gives you 2 over n pi cosinus of 1 cosinus n pi, sorry, minus 2 over n pi, the other integral. Right? So the first term is the difference between 0 and 1 of x cosinus n pi. X at 0, this is 0, at 1, it is 1 cosinus n pi. So the other term is 2 minus 2 over n pi, the integral from 0 to 1 cosinus n pi x dx. So how can I compute this guy? Yes?
It'd be 1 over n pi sine of n pi x.
Can you sign the back of the paper, please? So I take the antiderivative of this guy, I get 2 over n pi cosinus n pi minus 2 over n pi square of sinus n pi x, and I evaluate 0 and 1, because this is 0. So this gives me 2 minus 1 n pi n over n pi. Alright, so this is 0. Right. So you compute the second integral by taking the antiderivative of cosinus, which is sinus, but when you evaluate at 0 and 1, you get 0. The first term gives you 2 minus 1 of 2 power n over n pi, right? So basically, you have what? You have minus x is the sum when n is going from 1 to infinity of 2 minus 1 over n, 2 power n over n pi sinus of n pi x. Alright? This is minus x. Minus x will be the sum when n is going from 1 to infinity of 2 minus 1 to the n over n pi sinus n pi x. This is the Fourier series of minus x, right? And you know that u second will be sum when n is going from 1 to infinity of an minus n pi square cosinus n pi x plus bn minus n pi square sinus of n pi x. Alright? So this is what we computed before. U second is the sum when n is going from 1 to infinity an minus n pi square cosinus n pi x, bn minus n pi square sinus n pi x. And we just computed the Fourier series of minus x. The Fourier series of minus x is sum when n is going from 1 to infinity of 2 minus 1 to power n over n pi sinus n pi x. Alright? Now what can I say about an and bn? Yes?
That they'll be equal to Cn and Dn times lambda.
Sorry?
They would, An and Bn would be equal to Cn and or Dn times the lambda term.
Yes, but we know what we know Cn and Dn already, right?
Right.
So what is the explicit value of an?
0.
0, right? So you know Cn is 0 and Dn is this guy, right? So you just identify coefficient. Yeah. Can you sign the back of the paper, please? So you identify this guy and this guy because they have the same basis, right? And this guy has to be 0 because here you don't have cosinus. So you identify the coefficient, right? Identify the coefficient, right? So you're gonna have an is 0 because here Cn is 0. There's no Cn, and Dn is this guy. This guy is Dn, and you have Bn times minus n pi square is this guy, and Bn minus n pi square is 2 minus 1 power n dividing by n pi, right? It's clear, right? So the first step is to compute all of the basis, and the basis in this case is the Fourier series. So what I did here is to expand minus x in terms of the Fourier series, and this is what I get. I also expand u in terms of the Fourier series, and when I take the second derivative, I have some factor coming out. Now I identify them because minus x and u second are equal. So an times minus n pi square has to be 0 because here you don't have cosinus. And bn minus n pi square has to be equal to this guy because of the two sinus function, right? So which means that in this case an is 0 and bn is this guy. So bn will be 2 times minus 1 and plus 1 over n pi power 3. All right? It's good? Questions? Right, so coming back to the solution, right? The solution will be what? The solution will be a0 plus the sum when n is going from 1 to infinity of an cosinus n pi x plus bn sinus n pi x, right? So you know that an is 0, bn is this guy, so I plug it there. So the solution will be a0 plus the sum when n is going from 1 to infinity of 2 minus 1 and plus 1 over n pi power 3 sinus n pi x. A0 can be anything. You can put 1, 2, 3, 4, 5 there and you have a bunch of solutions, right? It's clear? So I explain again. After I expand the Fourier series, the minus x, the Fourier series of minus x is this guy, all right? You take the second derivative u, you get a Fourier series for u second. You identify the coefficient, you find that a0 is 0 because on the Fourier series of x minus x you don't have cosinus, and then you have bn minus n pi square has to be equal to this constant. I mean because they are the same coefficient of the same function. So an is 0 and bn is 2 times minus 1 and plus 1 over n pi to power 3. Now I plug it back to the original series of u. This a0 doesn't have any row, so I keep it there. An is 0, so I remove this guy. Bn is this guy, so I put it back here. This is the general form of the solution, right? And you can put any value for a0. You can put 10, and this is also a solution, or you can put 20, and this is also another solution. So you have infinite solutions for this equation. It's clear? Questions? So basically, this is what you have to do in the exam, right? So you have to do 2 eigenvalue problems to find the eigenfunction and the eigen values, and then you do this kind of expansion. Questions? It's good. So we still have 10 minutes. I can say a few words about the problem number 1, which is the optional one. But if you can solve it, you get another 10 points. Any questions on this eigenvalue and eigenfunction? Clear? So one, you solve the eigenvalue problem. Y second plus 2 y prime plus 2 is 0, y 0, 1 is 0. All right. So in the previous problem, I put it with phi. I put it with u. Now I changed the name to y, but it's the same problem, right? So what is the difference between this eigenvalue problem and the previous one? Yes. Yes. Can you sign at the back of the paper, please? So the difference between this guy and the previous one is the fact that here you have the first derivative. You have 2 y prime. All right. So this is much more difficult, but you still have to consider 3 cases. All right. The method will be the same. Basically, this is for all of the eigenvalue problem. There are second order differential equation with constant coefficient. What is the method that you use to solve second order differential equation? with constant coefficient and homogeneous. Yes?
It's all the characteristics of the
Yes. Can you sign the back of the paper, please? It's always the characteristic, yes?
Are we assuming that the lambda in that problem is the eigenvalue?
Yes, so
Lambda.
this is the eigenvalue and this is the eigenfunction.
So wouldn't that mean that 2y prime is 0?
No?
Right.
Why?
I'm just confused.
No, the eigenvalue is what? The eigenvalue problem is right, so the eigenvalue problem is, in the previous case, you have this problem, right? If you solve this problem, you have a series subsolution. And this series subsolution is called the eigenvalue and the eigenfunctions,
Right.
right? But you can change this operator. You can put this to be something crazy. And then you have private parameter 0 plus y parameter 1 to be 0. And then you have y0 plus y1 to be 0. So this is the boundary condition and this is the boundary condition. And here you add another derivative. So you solve this problem, you also have a series subsolution. And this series subsolution is still called eigenvalue and eigenfunctions. Right? It's clear? So you can, you can torture this problem and you can still have a series subsolution. Right? Alright, so this is the hard problem in the exam. Alright? So now what is the characteristic equation for this equation? Right?
R squared plus 2
Plus lambda is equal to 0. Inside the backup paper, please. Alright, so this is the hard problem in the exam. So I gave the solution in the paper. So if you read it and try to understand it, you can get an extra 10 points. Now, this is still an eigenvalue problem because you find lambda and a series of y such that this identity is satisfied. And you see that we find a series of solutions. This is solved by the standard characteristic equation method, which is x squared plus 2x plus lambda is 0, right? We have to consider 3 cases. What are they? Yes?
So just the 3 cases you put in?
No. This is a different problem, yes?
Would it be like after you take the, but you'd have the square root of 4 minus 4 lambda, and that would be delta, so it's if delta is greater than 0,
Yes.
equal to 0, less than 0.
So you take the delta, not the lambda. So the delta is so the delta is 4 minus 4 lambda. So lambda is positive, greater than 1, smaller than 1, and is equal to 1. Just have to make the paper, please. Now, so the delta in this case is 1. So remember that you have ax squared plus bx plus c in the table that I gave you. So the delta will be b squared minus 4c. And you consider the 3 cases. Lambda is positive, lambda is negative, and lambda is 0, right? Lambda is 0. All right. So the delta in this case will be 4 squared, 2 squared minus 4 lambda, and this is 4 minus 4 lambda. Right? You consider 3 cases. Lambda is positive. Case number 1. Lambda is positive, which means that 4 minus 4 lambda is positive, and this means that 1 is greater than lambda. So this is completely different from the previous scenario when you compare lambda with 0. But this is coming from this identity, right? All right. So case number 1, lambda is positive. So what are the 2 roots? Yes.
Minus 1 plus square root of 4 minus 4 lambda divided by 2.
Yes, can you say at the back of the paper, please? So the 2 solution will be, the 2 roots will be minus 2 plus square root of lambda which is square root of 4 minus 4 lambda divided by 2. This is minus 2 plus 2 times square root of 1 minus square root of lambda over 2. And this is minus 1 plus 1 minus square root of lambda. And the second root will be minus 1 minus square root of lambda. All right? Right? So then what are the two solutions in this case? Yes?
You go with the cosine and sine?
No. This is positive case.
Right, but we're gonna end up with an imaginary number because lambda is greater than 1.
No, lambda is smaller than 1.
Oh, sorry.
So what are the two solutions in this case?
C1 E raised to the power of x plus C2.
Yes, you can send the micro paper, please. So the first one will be C1 e to the R1x plus C2 e to the R2x. Right? And in this case, you're gonna have C1 e to the minus 1 plus 1 minus square root of lambda x plus C2 e to the power of minus 1 minus 1 minus square root of lambda x. All right, so this is the form of the solution. So what is the next step? Yes?
The boundary solution.
Yes, can you send the back the paper, please? So now you're going to plug boundary condition. And y1 is 0. So I don't compute this explicitly, but you see the solution and you see something like C1 is equal to C2 is 0. So the first case, you always get 0. All right? So I explain again. So here in this case, there are also 3 cases, but 3 cases will not be lambda positive, lambda negative, lambda 0. So we know that 3 cases for a second order differential equation with constant coefficient to have solutions are the cases when lambda is positive, lambda is negative, lambda is 0. Yes?
Is there a reason why you kept it as y and not b when you like turn into like I, you know, like problem?
No, it's just a name. It's just a name.
Oh, is it? Okay.
So you can put y, you can put phi, you can put a, b, c, whatever you want. It's just a name. Right? So in the first case, you plug the boundary condition inside, and you still find C1 is C2 is 0, right? So now case number 2, I have only 2 minutes, so I'm gonna skip case number 2 and I jump to case number 3. Delta is negative, right? So then, when delta is negative, what are the 2 roots? Yes?
Minus 1 plus or minus square root of 1 minus lambda I.
Yes, can you sign the back of the paper, please? So in the second case, you in the third case, you're gonna use this formula, but you put an I here, right? So R1 will be minus 2 plus I square root of 4 minus 4 lambda. In this case, lambda is bigger than 1 over 2. And in this case, you have minus 1 plus I square root of lambda minus 1. And minus 1 minus I square root of lambda minus 1. Right? I explain again. So for the third case, you wanna keep this solution, except that here this is negative, so you put an I and you put absolute value, right? So in this case, you have minus 2 plus I times the absolute value of 4 minus 4 lambda. You divide by 2, and then the absolute value of 4 minus 4 lambda is 4 lambda minus 4. So you can replace this. Yes.
Shouldn't lambda be less than 1 in this case? Because it was greater.
So this is the delta is positive, so 4 minus 4 lambda is positive, so this is 1 bigger than lambda. So this lambda is smaller than what is here. So this is negative, right? Right, so in this case, what are the 2 solutions? Yes?
C1 cosine and then actually never mind.
Right. So how do you? So this is not difficult, right? So you see the real part. The real part is always with the exponential. So you have e to the power minus p. The imaginary part will be with the cosinus. So this is C1 plus C2 e to power minus. Right? So in this case, if you look into a complex number like this, the real part will go to the exponential, and the imaginary part will go to the cosinus. And then the next one is to change cosinus into sinus. All right? And you plug this into the equation with the boundary condition, you find a series of lambda n, like in the previous case. All right? Yes?
Is there a reason why you use T?
Sorry. Yes, this is X. Can you sign the back of the paper, please? All right, any other questions? But this is the hard part. But the principle is the same, except that you have to know how to solve this. Yes?
So for case 2, we would just basically end up with R1 is equal to negative 1, right? And so then it would just be C1 is equal to 0.
Yes. So for the case number 2, it's going to be exactly like the previous case. And for the last case, we also have a series of solutions.